is George Laird talking, and I am the Principal Mechanical Engineer and also the Director of CAE and Applied CAX. And this is a technical seminar. If you haven't been to one of these before, it's pure technical. It's for simulation engineers. So this is me here, George Laird. And on the line, I also have Brian Kolb. Now, he'll be answering questions. So on these seminars, there's on the side, where it comes up, there's a little chat section, and you could post your questions there, and then Brian will answer them. And then also, of course, later on, you can always ping us an email and ask us more stuff. And all the stuff that I'm showing, and there's a couple deliverables and models, they're going to be posted on the web on Applied CAX in the coming week. So you can ping there and pick it up and send it on. So these seminars, we got a lot of material, we're punctual, we get it done, and we move on. We're quick. And now I have a message from my sponsor, because this is Applied CAX. This is our sponsor, and this is our team. There's about 30 of us all. We got life. Yeah. Is Jeremy there?
Yeah, I'm here. Sorry about that.
Excellent.
So yeah,
good. Hold on. I can introduce you. Okay. So this is Jeremy Russell. He's our account manager. He handles all things with a mesh, and he's very capable sorting things out. I'm going to turn the mic over to him to do his introduction before I get back to technical. Take her away.
Great. Thanks, George. Yeah, we're a team of engineers, right? So owned and operated by engineers that use the software that we support our customers with. So, we have 20 plus employees. Most are engineers, a few admins, and a few sales guys, myself and two others that focus on other products. But my emphasis and George's focus is on FEA and CFD. So, today's talk is about stress and fatigue with FEMAP specifically. Our big contribution, our big goal is to contribute to the community that we're part of. So George and Brian Kolb, our other technical resource here, create a ton of content because we want to give back to the community that we're a part of. So that's our main driver today. But our focus on the CAE side is FEMAP, STAR, SimCenter, and standing up our customers' use of those pieces of software. We want them to become proficient like we are, that we use it every day. And so our customers really lean on us for technical support because we use it and we find new ways, new workflows to kind of improve their use of those tools. And today is one of those scenarios where George is going to be talking about some things that you guys could probably leverage and learn and bring into your workflow and improve what you guys are doing. And so I just want to highlight that we are having a simulation symposium in February. We've actually just changed the date to the 13th, I think. And our keynote speaker is going to be Darrell Rittenberg. He is the director of aerospace within Siemens, handling simulation specifically with STAR. So he's going to be a great person to have at the talk. And if you guys are in the Northwest, in Seattle area, it would be fantastic if you could join us. We'll have some more information in the coming days to kind of highlight how you guys can join it. I just wanted to bring it back to George. But we're gonna have Brian Kolb, our other engineer here, answering questions. If you have any, you can just type them in the little question box here, and then we can get to them at the end or answer them during the seminar. But yeah, thanks for joining, and I'll give it back to George.
Thank you. Moving on. Like I said, all this material will be on the web a little time, sometime this week. Why we're here. Stress is easy, fatigue is scary. And I'm going to lay out a foundation, talk about stress, because if you don't have a good stress analysis, forget about it. I'm trying to do anything with fatigue. So this is the baseline. So we're going to first set up a foundation about talking about interpreting stress. You have your results, you have your model. Now you got the colors on the screen. So we're going to talk about what those colors mean and how they arrived onto the surface and how you can assess the quality of those results. So we start off with that. And then we get into fatigue and how do you interpret the stresses toward a fatigue analysis. And I sort of like this one. Are you chasing stress at a stress artifact? Sharp corners, fixural loading, point loading. And most of our clients have been in the stress world for a while and probably know that if you have a sharp corner, sharp corners don't exist in the real world. They always have a radius, but in the FEA sense, sharp can be infinitely sharp, and there is no convergence for loading. The stress just keeps going up. It's the same with the point loading. And if you had graduate course in mechanics, you know about the Bose-Einstein function for point loading, and it just asymptotic. We're gonna have to learn English one of these days. Asymptotic. It just keeps going up to infinity. The one is stress value robust. That goes into the accuracy of your numbers. How is your loads? How accurate are your loads? We all know it's one of those things. Loading, loading, loading. Three big things. How accurate that determines everything else. But I'm not going to talk about loading. I'm going to talk about interpretation of stress. So, and we're going to do the first order high cycle fatigue. Fatigue starts from surface defects, multiple stress states, what it means. And then, of course, what we don't cover, low cycle. This is where your stress is close to the yield, more than 80% yield, plastic damage, multi-axle. I mean, this is one of those things. Fatigue, I call it like the 80-20. 80% of understanding fatigue, really basic mechanics. Just keep it simple. And you got a checklist. If it falls outside the checklist, run to somebody that specializes in fatigue. And there's so much fatigue stuff out there for that other 20%. Low cycle, multi-axis, multi-load cases. And of course, people do their doctorates in fatigue all the time. But this is one thing. How do you know where the dividing line is where you can safely use fatigue, meaning 80%, don't worry about it, boom, boom, boom. Where I call it like in engineering, working within your profession, working within your knowledge bounds. And it's actually a legal term. If you're a professional engineer, you're required to work within your specialty in the sense of that you're competent. And that if you stamp a document, put your seal on it, it means you're working within your competency. So I think this little fatigue discussion today will allow you to say, okay, this is within my competency, or go find an expert to figure it out for that other 20%. What do we know? Why are we here? Why is this just not rambling? We've done lots of stuff on fatigue, lots and lots of stuff. It's been tested. It's been in the field. It's been running for years and years. And that's where I call the difference on a simulation engineer. It takes longer for you to get qualified because your mistakes have to catch up to you. Many people, you can bang out a model, done, look at that, fantastic. They can build it. They might pass initial prototyping and then goes into the field, but won't survive in the field. And that takes a few years to come back. So all these things, we've been predictive engineering now is going on 25 years. So we haven't had anything yet come back that we know of. So transmissions, pressure vessels, crankcases for motorcycles, gears, open pit mining, all these things involve doing fatigue analysis. And it's not, a lot of this stuff is as simple as looking at the stress and saying, it's low enough, it's not going to fatigue. Done, checkbox. Some of these are not so simple. This one in the seismic analysis was spreadsheets and spreadsheets and spreadsheets of summing load cases and directions and adding vectors. Hey, but it worked. Mining equipment, composites. Composites are another story of fatigue. It's another topic. I don't want to get into it. We could definitely spend time in the weeds on that. Okay, that's sort of our background, why we're here. Stress mechanics. When people get into it, we're using isoparametric elements to fill up shapes. And filling up shapes, random geometry, random surfaces, shell elements, isoparametric, solid elements, isoparametric. They're all using approximations to capture the deformation gradient through the structure. Finite approximations. So the isoparametric means it's using the same shape function to map the displacement at the corner nodes to the interior of the element. Then it can calculate strain inside the element. And then from that strain, you get stress via Hooke's law. So it's a two-step thing. So since you're using these approximations on an isoparametric element, and it's mapping everything, it maps it to a unity space, -1, +1 in the dimensions. So whatever shape your element starts out with, it always ends up being numerically mapped to unity, -1, +1. So of course, the more uniform your element, the easier the mapping, which is called the Jacobian to map it. The easier the mapping, and the easier the mapping, the more accurate the element in capturing the area for a shell or the volume for a solid, the more accurate, which translates to more accurate stiffness values, which translates to more accurate displacements, which translates to more accurate strains and stresses. So I bring this out. This is an article I did years and years ago. But it's always, this stuff is relevant. I mean, it doesn't matter. It's all the same, isoparametric elements and shape. And if it looks good, it is good. And the reason why I bring it up is that sometimes in our daily routine, we get so busy throwing something, getting a result, that we sort of blow through this of okay, what's our quality of elements? What are we looking at? And if we got to think about fatigue, it's time to step back and really think about it, because little tiny variations in stress can have a big effect on fatigue. So that's why we want to make sure we're interpreting data from a clean mesh. Brian, how you hanging out there?
Doing good. No questions so far.
No questions. How am I coming on audio?
Sounds great. Yeah. Audio.
Okay. And just checking. Did you catch my slurp of coffee there?
I actually didn't. Maybe
just checking. Yay. I know. This is, if you guys audience can't tell, this really is one of my favorite topics. I love all the mechanics stuff on it. And it's not a bunch of math. It's just unfortunate that most of the FEA textbooks out there are developed by mathematicians that masquerade as engineers. And they just love to just, like, all you see is equations out there, and you go, wait, I know this has some reality useful. So anyway, this article here will be part of the deliverable that will go on the web. So it's out there too. Okay, now that we've talked a little stress, I am going to show a model. I'm just not going to talk the whole time. Don't worry, I am going to show a new FEA map and a little thing, but I got to set some expectations. All materials have holes. All materials, seals, whatever, they all have defects. We all know that. We always start out with using a plate to show stress concentration, because plate with a hole. Yeah, it's all around. I always really like this graph with the lines. And of course, I got this from the website, fractionmechanics.org, but they're all over the place, these little drawings. And it's under uniform tension. You get the stress lines like that. And then one of those things, when you look at your stress, it should flow, because it's a biharmonic. That's another way you judge the quality of your stress results. Does it flow? Can you turn off the mesh and it looks smooth and groovy? And that's the way stress is, because it flows. It's a biharmonic. It's a partial differential equation. So on the right, we talk about what happens on the stresses around a hole. And you can see on the right-hand side, under tension, you get 300% magnifier. And at the very top, it goes under compression. You get a compression of 1. And what they're saying is, like, they do 1 to 300%, but it's a uniform tensile field in an infinite plate. So, and then it's a 3 to 1, 3 to -1. And this should ring some bells inside your head that, I got every structure that I ever worked on always have holes in it. And it should make you a little nervous about when you interpret your stresses under load, and a little concerned about stresses around holes. And in old school days, no one ever meshed holes because everyone knew. You look at your stress field and just take whatever stress you see and multiply by 3. And you knew. But now we got such power in our mechanics. It's like, oh yeah, we're gonna put that hole in there and it'll be teeny tiny. And oh, by the way, a buddy of mine was commenting about this specification to say, yes, we want to have 36 elements around the hole. You know, 1 element for every 10 degrees. And it was just like, you gotta be kidding me. You know, it was all solid elements, super complex, tiny holes everywhere. Yeah, I ended up some ungodly number of nodes. And this is all new. In the old days, you just look at the stress field. Yep, multiply by 3. Now, this is for a sheet, and this is standard mechanics stuff. If you have a hole in a solid, a defect, a void, it's not 3x, it's 2x under tension, and minus 1x at the top, minus 1x on the top. So if you have a hole, it's 2 to minus 1. Plate 3 to minus 1. And also it's cute too, is when you work in composites, a standard swag is, nope, we always knock down the properties by 3 and use that as our design limit. You know, whatever properties knock by 3 and you just use that. Well, of course, every composite structure I've seen has holes in it. So, but it's nice to see how all these engineering rules are developed. They're just based on mechanics, obvious mechanics. So, okay, let's play around a little bit. Let's do a little bit of stress modeling with FEMAP. And so this is a 2020.1. They got the new logo. And I know show tips, even though on tips, I sort of like to check and see what they're saying. So when I always have a new version, I always keep this on for a while, you know, before I give up and turn it off, and they can turn it off and stuff. And okay, this is our little play around geometry, and Control Q, because my default, I turn off geometry because I don't want to use it. You know, I don't need it. So we have a hole in a plate, and this is going to be our symmetry plane here. And with this structure here, since I'm going to give a uniform load across the top there, I have another plane of symmetry I can get rid of. So I'm going to go ahead and slice it down. I got to pick all like that. And okay, and this is one of those things you can just pick on the curve. It's got that intelligent pick on it. No, I got to undo. Sorry about that. Oh, I want to say, you know, don't be surprised if I'm not perfect on all these picks and you're going, why did that guy do that? Well, I don't practice these very much. I mean, I just ran through it very little because I don't like over practicing. I like doing it a little bit raw. And oh yeah, one of those things, preferences. That smart pick that I pick up, view, think, graphics, user interface. That's right there, smart, number 4 in your preferences. Oh, while we're here, I can't help but jump into views a little bit. And did you guys know that on the copy icon that you can scale your copy save by different factors? I set it to 2. So when you copy things to engineering report, it's twice the resolution on the screen. It makes things a little sharper on your graphics. Okay, so I slice it down through this. And now here's the question. Given the loading of pure uniform, given the geometry, is there another plane of symmetry in this model? Well, that's a standard, that's a real simple question. I'm not going to answer it. It's like one of those fundamental things. So let's mesh it. What do I got here? I brought it in as new. So I got to go in at first. I got to set the mesh sizing, and I'm going to use it. I'm going to show you how to use the new pyramid setup the little pyramid transition between hex and the other thing. And I'll set it, and I'm going to turn on the mesh sizing like that. Okay. Then I'll go in, mesh geometry. I'm going to hex mesh this part first. And I don't care. I'm just going to give it some steel like that. So there's our hex mesh. And for this part, I want it to transition. I want it to be 10 node tets up here. And I'm going to let it transition over. Check this out. I've been playing around with this. And I could use a glued connection too, but it's like, meh.
Hey, George, just to give you a heads up, things are a little choppy, so if you want to go a little slower, just to make sure you see it.
Thank you. I do need that.
Yep.
So this is new. This is set up. It will use a pyramid mesh. They'll transition between the hex into the tet. And I told it to go ahead and merge the nodes so I don't have to deal with it. And the logic behind it is that it knows that when I set up the meshing on this together as two parts, it set up a master-slave relationship between the two surfaces. So this solid here knows that there's a hex mesh on this side, so it knows how to do the transition like that. So, and it'll even tell you inserting pyramid mesh, and then it'll say a merge, and I'll go ahead and turn on the nodes here, and you can see how that transition worked. Is that in here we have our 10 node tet, and in here, and I'll go up to the selector, and I'll turn on element, and you can see the pyramid mesh right there, like that. So it's buried inside. There is a pyramid in there. I can't quite see it. So I'm gonna go back to turn all off and turn on geometry. And I think you guys know what I mean. There's showing the translucency between the two, shows that connection between the two geometries. Okay. So I'm gonna turn element loads, and I'm gonna turn on constraint like that. So that was a nice setup. So on this model here, I'm going to put a uniform load onto it, and I need to run it. So I'm going to do the load first. I'm going to not give it a name. I'm going to put it on a surface, and I want it to be the equivalent of 1,000 psi down on this section. And I know what the cross-sectional area down here is 0.05, and so, and I want to put it under tension. So I got to go the opposite direction on that, like that. And then on constraints is, this is one of the tricks I've been doing. I'm going to do nodal, but I'm going to pick based on coordinate. And it's that X direction right there that I want at location. Gives you a little pick right there. I'll pick that, say okay. That looks good. Hit the little view. Yep. There's my plane of symmetry that I want. Fix it in the direction normal. And I have my own little symbols I like to use and the colors. And I'll go right click, previous command. And I want to pick just on this surface here, right there. And that's going to be in the Z direction. So now I've defined the two planes of symmetry. I've tied it down in the X direction. I tied it down in the Z direction. And I have the 3 degrees. I have the 3 degrees of rotation constraint between the two surfaces. All I need now is one more node. I don't want it to fly off into space in the Y direction. It can't move in the Y like that, so I'll combine that. So I have the 3 translation and I have the 3 rotation defined. Okay, so now let's run this thing. Because I've defined a material, defined the elements, defined a load, defined a constraint. I'm done. I'll go to new. And I don't know if many people use this, but if you're dealing with a mesh that's dominantly 10 node tets, meaning it's very sparse. If it's very sparse mesh, the element iterative solution is quite fast. And you know, if you're dealing with solid elements, Nastran likes to print out these messages about that it's tied down the rotational degrees, grid point messages. Well, print grid point message. I'm going to turn that off. I don't care about that. And everything else is linear. So let's see if it's going to work, because I haven't practiced this far. I want to say this is my workflow. This is not something I'm doing for a demo. Yes, I could make it more simple for a demo, less clicks, but I don't like doing that. So here's the solver. Let's go look at the FO6 file. It ran, damn it, too fast. There we go, August 9, 2019, SimCenter Nastran 2019. And you guys know O load is going in, and it shows that we put in 50 pounds, a little round off error there. Then we have our SPC force result. Hey, that's what was calculated by the solver. That lines up. Everything looks pretty good. Did I get that? There's my result set, so I can close that out. So go into post-processing, go to contour, Nastran, solid. And now it's a little bit, I want to turn off everything I don't need. All off, turn on element. And it's higher than 3 because we don't have an infinite plate. And so even though it's 1,000 uniform through here, we don't have an infinite plate, so it's going to be a little higher, but got 3,200 there. And we know that, and it makes sense, but this is another thing. It's up here for the von Mises. You don't get a good idea because it just shows the other color. And I used to do this more often. I'll put this to node, and I'll put this to show tooltip. And what I want to do is I'm going to go into the results, contour options, and set it to nodal, because I'm picking on a node, and so when it contours, it needs to think about that the results are being at the node. So when you do that, you get this little thing. I used to do this more often, that it comes up, and then you can right click and convert to text. And it says 1,000. And then it goes off, and you go, what? What? You got to turn it back on. We'll turn it back on like that. 1,000 at the thing. But it's just von Mises, and we don't know whether it's positive or negative. And this is, I have one of these engineering quiz questions, like, what does it mean when your von Mises stress indicates is negative? And well, if you know how the von Mises is calculated, you'd be a little bit worried if you saw a negative von Mises. So now this is under tension. So what would be the stress at this point if the load was reversed? There's going to get a point to this. This is going to tie back into fatigue in a second. Is that we're always thinking of cracks and tensile. And if you work in stress mechanics, your first pass, von Mises, and then you contour the maximal principal stress, because things fail in tension dominantly. That's a big thing. So you look at the maximum principal stress and say, okay, what's the maximum tensile stress, and is that going to tear my structure apart? We don't often think about compressive loads that much, because we say, it's in compression, nothing fails under compression, right? There is no tensile stresses. Well, let's switch this around. Output, calculate. Let's do a tensile load. And yeah, I could reverse the load. Oh, I got picked the wrong one. I even put it in my notes, not, you know what not to pick? It's process. I got to change my notes. I put calculate. So I'm gonna do a linear combination, and I'm gonna scale it by -1, like there, and I'm gonna select my output, like that, there. I'm just gonna generate a new output set instead of rerunning. And then I'll go back into here, and there. I'll come up with a linear. And the von Mises stress, you see, it didn't change. Well, it can't. Von Mises doesn't know the difference between compressive or tensile. It just indicates the presence of stress. Oh, I hit F5. Yeah, you know, I'm so comfortable going here. Let me change the thing, you know, down here. And so it's like, oh, habits are hard to break. So it's like, no, I could use this fancy dancy thing right there. I'm gonna look at the solid max. And this is what I like to show. Under compression, remember I'm contouring the maximum principal stress. That's tensile. Now, we know that because when I was talking about the hole in the plate, I know everyone, not everyone, but most everyone was nodding their heads, yeah, 3 to -1, but not really quite getting the point of what's going on at the top of the hole. Well, under compression, if you have a pressure of a stress of 1,000 in compression, you're going to generate a tensile stress of 1,000 at the top of a hole. And it's whether a hole or whether it's a sphere inclusion or defect in a solid, it's going to be the same. You're going to generate this tensile stress at the top. Now, before I leave this, I want to talk about a little on stress averaging, because this comes up. And there we go. This still has utility. Dynamic, max min, so I can look at the stresses real quick, contour options. So I have it set to nodal. I'm going to turn it back to elemental, like that. On data conversion, it's averaging at the nodes. Each element is an island. Stresses are calculated at the Gaussian integration points, which means let's keep it simple, like a shell or a brick, which means that if we're dealing with a shell, we have 4 integration points: Nastran, ANSYS, Abacus, Ellis-Dyna. 4 integration points. 4 stresses are calculated there. And then they're extrapolated to the nodal points using the shape function of the element, or they're interpolated to the center of the element at the centroid. So for Nastran, each element outputs a centroid stress and 4 nodal stresses for all the components, and then they're averaged. Now, if we say don't use corner data, it's going to change, because you see how it dropped down? Because it's not extrapolating out to the edge, it's using data at the centroid. And one of the things I like to do, if I'm really sort of wondering about the quality of the stress, is I like to say what's happening at the centroid as compared to the nodal points. And these are average nodal stresses. And the element I picked, I hope the resolution works for you guys, but you have the centroid stress at the top, which says 800. And then you see the variation at the nodal points down below. And I think of that as the work that isoparametric element has to do from the centroid out to the edges. The most accurate stress that you have for an element is at its centroid, because it's interpolating from the integration points. So this is one of my judges that I use for the quality of the stress results, is how much work is being done between the centroid and the nodes. And people will also say, well, I'm in here, and some people say, no, I'm going to turn this back on. Say, I want to use the max value. Well, all it does is it looks at all the adjacent elements and say, well, what's the max value? See a little shift, because now it's pulling the max value. I don't subscribe to that theory of it being more conservative, because knowing how elements are calculated and the numerical formulation is, the max value could be a little tweak, a little badly formed element, or a little bit, it's usually not a quality value. And when you average, you're pulling in the best, you're averaging to a better mean of value. So really, FEMAP is geared up on the default to be the best approach, as far as I can figure, is that you would never want to change it. So, but people do. I mean, some, no, I want to use the max, and they make these long discussions. Fine, keep it. Enjoy your party. Okay, this is what I wanted to use this model for. I wanted to talk about stresses around the hole and emphasize that how it changes at the top. I wanted to introduce the transition meshing at least, show the 2020.
George,
And you guys,
sorry to interrupt.
yes?
The transition
No,
message,
please.
we had a quick question. I'm pretty sure it does, but do the pyramids work for both mid-side TET meshes or without the mid-side node as well? I didn't play around with that yet.
I didn't quite catch that. I heard somebody banging on the table and something else.
Sorry. I was asking if the pyramid meshes work for mid-side TET meshes, or can you use it without the mid-side nodes as well?
Yeah, on the pyramid mesh, what they're doing is that it's just a blend at the interface.
Right. So it works for both.
Right, and they suck. I mean, anytime you have a change in element formulation, you're talking about a change in the shape function of the element. And would I ever put a pyramid in a high stress region of interest? No. I mean, would I even do a hex to a TET or a glue trans in a region of high interest? No. But
yeah,
heck,
the question specifically was, does it work with mid-side TET meshes? Or
yeah.
mid-side?
Yeah. Because what it does in the back is it'll rip off nodes and it maintains continuity along the merged edges. So what it'll do on a 10 node TET is it'll remove a mid-side node to maintain continuity with the pyramid. If the pyramid doesn't have a mid-side, if the pyramid has a mid-side, it'll blend it in. I'm pretty sure, I'm 80% confident on that one. And it's like a lot of things people say, well, how do you get more confident? Well, you know my answers. If you've worked with me, you're going to say, I build a small model and I look at it. And how close to a region is important. And if you work with me, you know the answer. I build a small test model and I look at it. How does the transition? I build a small model and look at it. So there, because it's mechanics and there's no one. It's hard to say there's a right answer exactly. Okay, I've had my fun with this. This is good. So these are some stress mechanics to think about. Under tension, talked about that. Tensile compressive, stress converge. I talked about nodal, centroid nodal. This is really, you can tell it's notes to myself. Good, I caught that. Oh, it turned on my email process. I thought I was so clever. Okay. Yeah, I got to turn off my email. Okay. Now we're ready to talk about fatigue. This little white paper is part of the deliverable. It'll be there if you want to pick it up. And I cut out the pages of interest. And we're going to talk about high cycle fatigue. I'm not going to mess around with anything in low cycle, stress over 80% of yield. High cycle, clean. There is no plasticity to worry about. 80% of yield. High cycle, because low cycle, anything under 10,000, you're not going to have any damage. It's all good to go. This is part of the thing, knowing your cycles. So, and this is my quick and easy overview because we only have another 22 minutes, so I can't get too things. I like this. Why is fatigue sneaky and feared? Because, well, it's this. It's the stress concentrations. It's the holes in your material. People go, wait, I built this beautiful model, and the stresses are 80, 60% of yield, and I don't have to worry about fatigue. Well, as you know from the prior mechanics, anywhere you have a tensile, if you have a tensile field, if you got a solid material, just double your stress. Just double it. You just know that somewhere there's a void and it's going to be double. And then people say, well, the load's mostly compressive. I don't have to worry about that as compressive. Well, you now know under compression, if you have a defect, a void, an inclusion, that you're going to have a tensile stress equal to the magnitude of the loading. And I think this is quite good because being a material scientist for many years, you could, and running tests, you could take a material, you could just squeeze it down, like a stainless steel is like butter. So you can squeeze it down to foil, and it wouldn't break. But it all depends on the purity of your material. But for materials that have any sort of voids, when you start to squeeze them down, you get this shearing. You get this sort of boom effect where they shear through. And under fracture mechanics, nothing should ever fail under compression. But if you know about defects, stress concentrations, you go, well, heck, of course, at the top of any defect, you're going to get a tensile stress normal to the loading. Or let's say perpendicular to the loading. So you push down any defect, you're going to get a tensile stress perpendicular to that load field. So that's why when you put materials under compression, you can see them pop to the side, because that's where the crack is going to initiate. It wants to run up from the defect. Once it finds a defect, it creates a crack. That's an automatic defect, normal stress. So you could also say a rule of thumb is, well, under compression, really, I can double up the load 2x than what it could stand for tensile. If it survives under tensile at 50, we could easily handle a 1x, so to speak, under compression. So this is the sneaky part. This is why for a lot of structures where things you don't quite think about it thoroughly, you find out they fail under fatigue with high cycle, because one doesn't really consider everything defects, stress concentrations, everything is 2x under tension. So, and it doesn't matter your material, because on fatigue, you're moving dislocations, and dislocations is a crystal structure, is plastic deformation. But if you're at 50%, you're going to have stress at yield in your material, because it's 2x for a void, if it's a hole in a plate, 3x. So you're going to be moving dislocations. And when you start moving enough of them, they bind up, they form a little micro crack. And voila, there goes your structure. The little graph in the corner is fatigue limit, shows aluminum. There is no fatigue limit, but most people say, hey, look, we don't need trillions of cycles. We're happy with a couple million. So that's usually how you design for aluminum. You set your limit, fine. Steels actually do have an endurance limit. And to let the cat out of the bag, you guys know now why endurance limit for steels, it's usually 50% of yield. It's simple. Keeps it simple. But even at 50% of yield, you know you're going to have yield at defects. And that's where dislocations will grow, and that's where cracks will start. But it's quite slow. Quite slow. And that's why you have the endurance limit. So now you have enough, you have a basis, you're comfortable about your stress number, you understand statistically the variation in your loads, you're comfortable about your loads, you're comfortable about your stress that you're pulling out, and for fatigue, it's all about the surface, because usually you got bending, and bending creates maximum stresses at the surface, not the inside, surface. So now you looked at your stress, and you're comfortable with the stress field, and it's smooth and groovy, and it's got everything there, and you say, okay, I'm ready to start really looking at fatigue, and it's on the surface, and you're okay. What else should I cover? I know about defects. I understand that. I understand where I got to go. Surface. Well, surface has defects. Stress concentration, surface roughness, and so there's been lots of really nice work done on the effects of surface. And I like this one brutally simple figure in the left. This is out of Julie Bannatyne, my favorite fatigue book. At the end, I'll show you the reference for that. And I'm sure she got it from somewhere else. It's a reference in her book, but it shows where the strength of your materials for steels and the surface roughness. And the thing on the side, the surface factor, is your stress, is you take your stress and divide it by that number. So let's say you see a stress in your model, and it's 100,000. And your yield strength is 200,000. I'm keeping it simple. 200. You got 100. So, and let's say you had a surface roughness somewhere where the surface factor was 0.6. So then you would take your 100,000, divide that by 0.6, and your surface stress for fatigue, would be 140,000, roughly. Hey, Brian, did I get that right? 100 divided by 0.6?
I think so, yeah.
I think so, 140. So anyway, your stress that you would use for your fatigue calc would be 140,000. And this is one of the things, you talk to people that do fatigue and say, well, what do you use for surface roughness? I just multiply. I just use 0.6 for everything. Engineering practice, huh? And this is one of my favorite sayings. The difference between a simulation engineer and a design engineer is that design engineers get second chances. Because as a simulation engineer, we are the last step before someone builds a prototype. And so if we don't get it right and they build the prototype, it's really expensive. And then everyone starts questioning your models. It's nonstop people throwing peanuts at you. So when I come out of the gate, it's conservative, conservative, conservative. And if it passes, it's like, hallelujah, hallelujah, it passed. It's like, good. If it doesn't pass, then I have to start whittling away at margins, and I get buy-in from the team. Like, are you comfortable with this? I got to cut back on this margin. I got to cut back on that margin. But I always go out of the gate. So that's why you might have seen somewhere in your practice that people will take your FEA stress and now just whack it, multiply it by 1.4 to use for the fatigue count. So we also have to deal with mean stress. It's alternating. So I want to, at this pause right there. Okay, so this is going to be the cyclic. What I'll do, a lot of times people say this is one load case, and we know we're going to have 100,000, 200,000 cycles. And the surface roughness, I'll just take the stress state, multiply it by 1.4, cross my fingers and hope it's at 50% of yield of the material. And if it is, just stamp it. Done. Infinite life. Go home. One load case. Look at the stress. Look at the surface finish. Multiply 1.4. Up. Under 50% yield. Stamp it. Go home. I wish everything was that simple, but it's not. So then you have these cases where you have alternating stress, the classic, but with a mean stress in it. So it's elevated. And that can't be good, but it's not the end of the world. It's just not as good. And so this is where I get it more into the paper, and I don't want to get too deep into the mean stress effects because you need to work it out with a piece of paper and a pencil and in your own quiet little, space and figure it out, because trying to gloss over it in 12 minutes is a little bit brutal. But let me do a really high level discussion on it. Is that fatigue data comes from multiple specimens that are nicely polished, that are fully reversed, up, down, up, down. They call that R-1. Fully reversed. Now, when you add, and then you get these graphs on the top, but when you add mean stress to it, the curve shifts downward, meaning, and you put into the fact of mean stress, your fatigue life is less. I think that sort of should make obvious sense, right? The effects of positive mean stress is going to shorten up your fatigue life. That's like, I call that the engineering, feel good engineering, like, oh, yep, that makes sense. The math is just algebra. It's pretty simple. Smith, Watson, Topper. You just figure out what your mean stress is, and they got all the formulas, and you take your R-1 data and you can adjust it down to figure out where to go. And then, of course, there's a Miner's rule for adding up your damage and stuff, and it's not that hard, and you got your MMPDS for fatigue life, adjustment, and I call it think statistically. Nothing is ever a perfect call. That's why I like like this raw data because it shows you the scatter, and they show you how you put in the curve. It gets you thinking like, you know, what does that curve really mean? And what it really means is when they plot it, it's like you're at the 50% margin and outliers. So people that have to deal with these curves a lot that are the experts, they say, nah, we never lose that mean curve. We always back it off to the side. You know, we always take some fraction of that, back it off a little bit for more margin. And all these little, and I think of it as like really cute. You got to put a little statistical Gaussian distribution on the curve. And you use the data. So dealing with mean stress and understand a lot of this, you can find in Dr. Bannatyne's book. And it's still in publication, I'm pretty sure. I actually downloaded a PDF off the web. And it is really nice, really straightforward. And of course, there's tons of material out there. Let's wrap it up. Accurate is your stress calc, duh. Little variations in stress, got little variations, we know that. All materials have defects. Think statistically. Don't use the line, you know, there's just always start out conservatively, then tighten it up. Infinite life, half yield stress is well grounded, and metallurgical reality, all defects, and engineering mechanics. Why compressive stress is bad. And I like to say this out too. You made it. Congratulations. You now know more than 90% of your colleagues about FEA stress interpretation and the fundamentals of fatigue. And I'm sure you could use this for engineering credit. Professional development unit of an hour for you guys that have to do your PE stuff. And if you read through some of these materials and stuff and send me a note, I'm sure we can give you a couple more PDU hours. That's it. Thank you. Look at this, 9:22.
Yeah, I think no questions. So I think everything's
They're
good.
all sleeping. Oh. So, you know, I had one of the things I was going to say.
There's a quick question just popped up here. It says, you mentioned that fatigue modeling of composites has some differences from isotropic solids modeling. Would you be able to touch on some of these differences? Assuming that's probably a pretty topic in and of itself.
No, because it's so chemical. The glass is a glass, it just pops. And then fatigue on the composites, as you can guess, it's all about the interfacial chemical bonding between the fiber and the goo. And that's why Toray Chemicals out of Japan sort of owns the market, because they have the special sauce on their glue, on the epoxy, to maintain interfacial shear strength on it.
Sounds like, do you have any of the references for those that maybe we could include?
No, I'm not going to do it. No, I'm not going to touch that one.
All right.
That's a whole, you know how it goes. It's like,
yeah.
Here, take this. And then people are going to ask me more questions.
Fair.
Yeah, composite. I was going to say on this model here, it's like if you didn't know where the other plane of symmetry was obvious, it's like, well, it was like this talk I heard at this little private university in Palo Alto about actuarial statistics on life expectancy. And so the guy was going to talk about all these things that affect your life expectancy, you know, like driving a motorcycle, jumping out of an airplane. And he said, for all you guys that smoke cigarettes out there, you can just leave right now, because everything I'm going to talk about, it has a much less statistical chance of killing you than jumping out of a plane. Thought that was funny. It's like and it relates to the mechanics here. It's like if understanding the symmetry of components isn't just like first order obvious in your head, then everything else that I'm going to talk about is too complex. That's why I always like to start with the foundation and know that really, really well with no doubts, because then you have a base to jump off of. So, okay, well, I have no problem. No other questions that side. And this will be posted up on Applied sometime this week. And Jeremy Russell, my account manager, if you have any questions on software, documentation, that stuff, talk to Jeremy, because he's the holder of all that stuff on licensing, trials, things like that. I try to keep out of it because I'm the propeller head. I'm the simulation engineer. And
I'm here, guys. So anytime you need to reach out about anything, feel free to.
Yeah, and this will be February 13th, and the speaker will be he's really fantastic. He has tons of industry experience, shows all these examples and stuff. And if you're not aware of this is really pain field. And it's like a hop, skip, and a jump over to the flight center. It's I don't know, like a 2-minute taxi drive thing. And we're also going to have a social hour afterwards, free beer, drinks, so you can socialize with the people that come and network. Bring your business cards, bring your resume, things like that. You never know who you want to work for on the next job. And I understand, you guys are on the West Coast and stuff, but it's easy to fly in. There's a hotel right there in the field. We're going to be staying at the hotel. So what the hell, you can turn it into like a networking party, because we're going to be drinking after this event, and we're going to go have dinner. And then there's going to be more party afterwards. And then you can come and get completely hammered, and you fly out the next morning or spend the weekend in Seattle. Right on. Any done? Shut her down?
Yeah, I think we're good.
Yeah.
Right
Thanks
on,
everybody
guys.
for coming.
Thanks for coming out.
Thanks, George, for presenting. That was good.
Very welcome, team. Okay. Take care. Have a good day.
Take care, everyone.
Bye-bye.